Hello? I didn't see you there. Do you have these loud neighbors who goes all day long making loud noises? You can hear them going to the bathroom, watching TV, and then, at night, these loud, excessive dinner parties. Every day.
Well, it so happens that we have been studied the acoustic properties of a certain type of wall. This wall is called a double-leaf wall. And you may ask, what is a double-leaf wall? In your standard interior wall, you often find some kind of wooden framework enclosed by boards, usually made out of gypsum. Depending on the number of sheets, you may call them single-leaf wall, double-leaf wall, triple-leaf wall, or even quadruple-leaf wall. In this project, we of course study the double-leaf wall. Over to you, Mike.
Oh, well, thank you. In this project, we're going to study the performance of the double-leaf wall, varying the parameters within. We're going to first of all vary the distance between the vertical studs, followed by the distance between the boards, and then finally varying the number of boards on each side. Back to you.
In order to analyze these walls, we will use the finite element software Abacus. We will jump straight into Abacus, where we model the different parts of the structure. We create the wooden frame. We also create the air cavities, and we create the plasterboard. The parts are given material properties and are then assembled to the final structure. Boundary conditions are applied, and we restrain movement in both translational and rotational movement along the outer edge of the structure. Some interesting information about the structure when making dynamic calculations are the eigenmodes and eigenfrequencies. These are calculated in the program, and here you can see the first eigenfrequency at 23.5 Hz. Another mode of vibration is found at 35.6 Hz. Another one, for example, is found at 50.8 Hz, and the list goes on and on and on.
The performance of a wall is preferably measured in sound level reduction in terms of decibels. This requires that the receiving room also has been taken into account, which has not been done in this project. Results in terms of sound pressure level will therefore not be obtained. What can be measured, however, is acceleration caused by an excitation source. In this case, a frequency sweep will be performed by applying a concentrated force on one side of the wall and specifying a span of frequencies. After the simulation, acceleration at each frequency will be measured on the other side of the wall. This will be done for the different wall configurations to be able to make comparisons. The accelerations for the reference wall is seen in this diagram. Here we can clearly see that the accelerations increase at certain points. These are the resonance frequencies of the structure. Some of these were shown before, for example the one at 23.5 Hz. When we increase the number of the vertical wooden studs, we can do the same analysis as before and compare with the reference wall. The values of the accelerations are shown here in a pinkish color. For this case, the resonance frequencies are fewer and show smaller acceleration amplitudes. This means that this wall is generally better in terms of reducing the vibrations. This is probably due to the fact that the stiffness of the wall has increased.
Another variation was to increase the thickness of the entire wall, meaning that the vertical wooden studs and the air pocket will be bigger. In the diagram, we compare a stud depth of 120 mm with a reference 70 mm. It seems that the resonance peaks have been shifted a bit due to the increased stiffness. At low frequencies, the amplitude of the acceleration stays pretty much the same in comparison with the reference, but for higher frequencies, the acceleration seems to decrease.
In the case of double sheets of plasterboards on either side of the wall, the sound reducing performances in the higher frequencies are generally better than for the reference wall, though there is one very major peak at 90 Hz that you may be concerned about.
In conclusion, it is evident that changing the geometric properties of a wall will affect the vibration response. From the simulations, it is shown that making changes that increase the amount of material, especially wood, usually is beneficial, though problems still exist at resonance frequencies. When constructing a wall that is sensitive to vibrations, it will be useful to know the frequency of the excitation source, and then pick a wall that does not resonate at that frequency. The results in this presentation were just shown briefly. An interested engineer can read more about our findings in the final report, which should be available right now. A final note concerning computer simulations is that they can be somewhat complex and often error-prone, which may or may not result in chaotic breakdowns.